Hi, this is the second tutorial in the Cellular Respiration series. In this video, we are going to look at glycolysis. Glycolysis is the process of breaking down a glucose molecule into pyruvate and gaining a couple of ATP and NADH in the process. Glycolysis begins with the molecule glucose. The enzyme that begins this process is called hexokinase, or glucokinase in the liver. A kinase is an enzyme which adds phosphate groups onto things by taking them off an ATP. And that's exactly what happens here. An ATP donates a phosphate to the glucose and creates this molecule, glucose 6-phosphate. It seems odd to use ATP in this process because we are trying to create ATP, but we'll see that we get all this ATP back plus more once the process is complete. The glucose 6-phosphate is acted upon by phosphohexose isomerase. Isomerases are enzymes which rearrange the structure of the substrate without changing the molecular formula. We can see that the phosphohexose isomerase rearranges the glucose 6-phosphate into a fructose 6-phosphate molecule. Now we meet another kinase, phosphofructokinase 1. This enzyme attaches another phosphate group to our molecule, creating fructose 1,6-bisphosphate. Sorry, my mistake, that should read fructose 1,6-bisphosphate, not bisphosphonate. Anyway, moving on, the molecule is then split in half by fructose bisphosphate aldolase. An aldolase is an enzyme that creates or breaks carbon-to-carbon bonds, which makes it the enzyme of choice to split the fructose 1,6-bisphosphate molecule into these two molecules, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. The next step is conducted by another isomerase, the triose phosphate isomerase, and this converts the dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. The next enzyme we meet is glyceraldehyde 3-phosphate dehydrogenase. The dehydrogenases move a hydride ion, that is H-, onto an electron acceptor such as NAD+ or FAD. This is what happens here, creating two NADH. There are two molecules of NADH created because one glucose molecule created two glyceraldehyde 3-phosphate, one from the aldolase reaction and one from the triose phosphate isomerase reaction. The hydride group on the molecule is replaced by a phosphate group supplied from inorganic phosphate, not from ATP. It is the reduction of NAD+ into NADH which provides the energy to bind inorganic phosphate. This gives us the molecule 1,3-bisphosphoglycerate. Here the molecule meets another kinase, phosphoglycerate kinase. We saw above that kinases can giveth phosphate, but they can also taketh phosphate away. And that's exactly what happens here. Two ATP are produced by taking phosphate from the 1,3-bisphosphoglycerate molecules. This produces the molecule 3-phosphoglycerate. The enzyme phosphoglycerate mutase is essentially an isomerase, so it creates the isomer 2-phosphoglycerate from 3-phosphoglycerate. Enolase is the next enzyme and it produces a double bond by removing the hydroxyl group. This leaves us with phosphoenol pyruvate. The final enzyme of glycolysis is pyruvate kinase. And this kinase is also going to remove phosphate groups from the molecule, attach them to an ADP and create ATP. Again, two of these are created because two phosphoenol pyruvates will be created for every glucose molecule. This finally leaves us with pyruvate, which will be the substrate for the TCA cycle. Now for your reference, I shall quickly number these steps, and you can see that there are 10 steps in total. Steps 1 to 5 are often referred to as the investment phase because they use up ATP. Steps 6 to 10 are known as the payoff phase because we get back our initial 2 ATP investment plus 2 additional ATP and 2 NADH, which will later become even more ATP. And that's glycolysis. In the next tutorial, we will be having a look at the fate of pyruvate as it enters the TCA cycle. If you've enjoyed this tutorial, please help us produce more by making a donation at www.handwrittentutorials.com.